Hi, myself, I'm Mohammed Sahel, Department of Mechanical Engineering, third SEM, and the subject is Material Science and Engineering. Subject code is BME 303 from SVC Bangalore. Today's topic is Physical Metallurgy. Physical Metallurgy, Introduction to Physical Metallurgy. Physical metallurgy is the study of physical properties and structure of metals and their alloys. It combines principles from physics and material science to understand how metal behave under various conditions. This field is critical for development of new materials and improving existing ones. Let's move on to the importance of physical metallurgy. Physical metallurgy plays a vital role in the manufacturing industry by enhancing material performance. Understanding the microstructure of materials helps engineers design components that can withstand specific stresses. It contributes to innovation in technology such as lightweight materials for aerospace applications. Next, we move on to the basic concepts of metallurgy. Metallurgy encompasses passes the extraction of metals, their processing, and the study of the inherent properties. The field is divided into two main branches: physical and chemical metallurgy. Physical metallurgy focused on the relationship between the physical structure of metals and their mechanical properties. Next, we move on to the atomic structure of metals. Metals have a crystalline structure that describes their physical properties. Like in this picture we have things like silicon and oxygen and the atomic structure. The arrangement of atoms in a metal affect its hardness, ductility and conditional, like salt crystals, chlorine and sodium in this atomic structure. Understanding atomic structure is crucial for predicting how metal will behave under various conditions. In ice crystal, oxygen and hydrogen. These are the atomic structures which are present in atomic structure of metals. Next, we move on to the types of crystal structure. The most common crystal structure in metal include face-centered cubic, body-centered cubic, and hexagonal close-packed. Each structure has distinct properties and influence the metal performance. The arrangement of atoms within these lattice affects slip system and deformation behavior. Next, we move on to the phase diagram. Phase diagrams are graphically representation of the phases present in a material at different temperature and composition. In this phase diagram, this diagram explanations this temperature and the pressure of the movement takes place and the sublimation and deposition, triple point, gas condition, boiling and condensation, where the critical point takes place and the melting point takes place, where the solid and liquid and the supercritical fluid. Engineers use phase diagrams to determine optimal processing conditions for alloys. Next, move on to the solid solution. Solid solution occurs when one metal is dissolved in another, resulting in a single phase mixture. In this picture, we get to know the substitution solid solution, where solvent metal atoms and solvent element atoms. In next image, we get to know the interstitial solid solution, where the solid solvent metal atoms and solute of element atoms. The solubility limits defines the maximum concentration of the solute that can dissolve in the solvent. The solid solution can significantly alter the mechanical properties of the base metal, which in this image shows the crystal packing, intermirrors, conglomerates, and active components. Next, we move on to the alloys and their classification. Alloys are a mixture of two or more elements where at least one is a metal. They can be classified as a substitutional or interstitial based on the solute position within the metal lattice. Understanding alloy system is crucial for tailoring metal properties for specific application. This image shows the alloy definition and example, like bronze, copper 78 to 95 percentage, tin 5 to 22 percentage, and gold 18 carat gold. Gold has 75 percentage, copper 12.5 percentage, silver 12.5 percentage. Brass contains copper 60 to 90 percentage and zinc 10 to 35 percentage. Cast iron 96 to 98 percentage, carbon content 2 to 4 percent. And next we move on to the heat treatment process. Heat treatment process is a controller process used to alter the microstructure of metal, enhancing their mechanical properties. Processes like annealing, pinching, and tempering are commonly employed to achieve desired characteristics. The effectiveness of heat treatment depends on the alloy compositions and initial microstructure. In this image, the image represents the hardening and tempering treatment process, where the inductor workpiece, alternate surface layer, water nozzle, feed, hardened surface layer. Next, move on to the mechanical properties of metal. Key mechanical properties include tensile strength, yield strength, ductility, and hardness. These properties are influenced by the metal microstructure, compositing, and processing methods. Understanding these properties is essential for application in construction, automotive, and aerospace industries. This image shows the mechanical properties. Mechanical properties are of stiffness, strength, ductility, toughness, resilience, and hardness. Stiffness says that elastic modulus or Young's modulus. Strength says that yield ultimate factor proof offset yield measured as stress. Ductility measure of ability to deform plasticity without fracture, elongation area reduction fracture strain. Toughness resilience says the measure of ability to absorb energy. Hardness says that resistance to indentation various scales. Next we move on to the deformation mechanisms. Deformations in metals can occur to processes such as slip, pinning, and grain boundary sliding. Slip is the primary mechanism for permanent deformations under applied stress. The ability of a metal to deform depends on its crystal structure and the presence of delocalization. Next, we move on to the delocalization and strengthening mechanism. Delocalization are defects within the crystal structure that significantly influence a metal mechanical behavior. By strengthening mechanisms like work hardening, solid solution strengthening, and grain refinance are based on the controlling dislocation movements. Manipulating these mechanisms allows for the designs of storage stronger materials for various applications. Next, move on to the fatigue and fracture mechanisms. Metals can fail due to fatigue, which is the result of repeated loading cycles. Understanding the mechanisms of cracks, initiation, and propagation is crucial for preventing structural failures. Fracture mechanisms helps predict how material behave under stress and can guide design improvements. This image says that the fatigue and the fracture mechanisms, how it works, how it works. Next, we move on to the application of physical metallurgy. Physical metallurgy is applied in various industries, including aerospace, automotive, and electronics. That the field enables the design of materials that meet specific performance critical such as weight reduction and increased strength. Application of physical metallurgy continue to evolve with the advancement in technologies and material science. Next, we move on to the emerging trends in physical metallurgy. Research in physical metallurgy is focusing on the development of smart material and nano-structured alloys. Additive manufacturing techniques are changing how materials are designed and produced. Sustainability and recycling of metals are becoming increasingly important consideration in metallurgy. Next, we move on to the future directions in physical metallurgy. Future of the physical metallurgy lies in the developing materials like with enhanced properties for specific application. Collaboration between academics and industries will drive innovation in metal designs and processing. The industry will increasingly focus on the sustainable practicals and life cycle assessment of the material. Next, we move on to the conclusion of the physical metallurgy. Physical metallurgy is a dynamic and essential field that influences various industries. A solid understanding of material properties and behavior is crucial for engineering and scientists. Ongoing research and advancement will continue to shape the future of the material science. For the reference content, these are the book which are written by the Callister W.D. and Material Science and Engineering and Introduction and the Elements of Material Science and Engineering. Thank you.